Assalamu alaikum. Let's start lecture number 19 of CS 317 Operating Systems. Today we start a new chapter called IO Management, and we will use chapter 11 of the William Stallings book for this topic. The first subtopic of this chapter is operating system design issues relevant to input and output devices. Design objectives. Two objectives are paramount in designing the IO facility: efficiency and generality. Efficiency is important because IO operations often form a bottleneck in a computing system. Most IO devices are extremely slow compared with main memory and the processor. One way to tackle this problem is multiprogramming, which allows some processes to be waiting on IO operations while another process is executing. However, even with the vast size of main memory in today's machines, it will still often be the case that IO is not keeping up with the activities of the processor. Swapping is used to bring in additional ready processes to keep the processor busy, but this is an IO operation itself. A major effort in IO design has been schemes for improving the efficiency of IO. The area that has received the most attention is disk IO. Generality. For simplicity and freedom from error, it is desirable to handle all devices in a uniform manner. This applies both to the way in which processes view IO devices and to the way in which the OS manages IO devices and operations. Because of the diversity of device characteristics, it is difficult in practice to achieve true generality. We use a hierarchical modular approach to the design of the IO function. This approach hides most of the details of device IO in lower level routines so that user processes and upper levels of the operating system see devices in terms of general functions such as read, write, open, close, lock, and unlock. Layered organization of the operating system. The hierarchical philosophy is that the functions of the operating system should be separated according to their complexity, their characteristic time scale, and their level of abstraction. Following this approach leads to an organization of the OS into a series of layers. Each layer performs a related subset of the functions required of the operating system. It relies on the next lower layer to perform more primitive functions and to conceal the details of those functions. It provides services to the next higher layer. Ideally, the layers should be defined so that changes in one layer do not require changes in other layers. Thus, we have decomposed one problem into a number of more manageable subproblems. In general, lower layers deal with a far shorter time scale. Some parts of the operating system must interact directly with the computer hardware, where events can be as brief as a few nanoseconds or a few picoseconds. At the other end of the spectrum, parts of the operating system communicate with the user, who issues commands at a much more leisurely pace, perhaps one every few seconds. Logical structure of the IO function. Applying the hierarchical philosophy specifically to the IO facility leads to the organization shown here. Most operating systems approach I/O in approximately this way. Let us consider the simplest case first, that of a local peripheral device that communicates in a stream of bytes or records. The following layers are involved. Logical I/O. The logical I/O module deals with the device as a logical resource and is not concerned with the details of controlling the device. The logical I/O module is concerned with managing general I/O functions on behalf of user processes, allowing them to deal with the device in terms of a device identifier and simple commands such as open, close, read, and write. Device I/O. The requested operations and data, buffered characters, records, etc., are converted into appropriate sequences of I/O instructions, channel commands, and controller orders. Buffering techniques may be used to improve utilization. We will talk about buffering somewhere later in this lecture. Scheduling and control. The actual queuing and scheduling of I/O operations occurs at this layer, as well as the control of the operations. Thus, interrupts are handled at this layer and I/O status is collected and reported. This is the layer of software that interacts with the I/O module and hence the device hardware. Now let us look at a communications port. For a communications device, the I/O structure looks much the same as for a local peripheral device. The principal difference is that the logical I/O module is replaced by a communications architecture, which may itself consist of several layers. An example of a communications architecture is TCP/IP. Here we show a representative structure for managing I/O on a secondary storage device that supports a file system. The three layers not previously discussed are as follows. Directory management. At this layer, symbolic file names are converted to identifiers that either reference the file directly or indirectly through a file descriptor or index table. This layer is also concerned with user operations that affect the directory of files, such as add, delete, and reorganize. File system. This layer deals with the logical structure of files and with the operations that can be specified by users, such as open, close, read, and write. Access rights are also managed at this layer. Physical organization. Just as virtual memory addresses must be converted into physical main memory addresses, considering the segmentation and paging structure. Likewise, logical references to files and records must be converted to physical secondary storage addresses, considering the physical track and sector structure of the secondary storage device. Allocation of secondary storage space and main storage buffers is generally treated at this layer as well. Our next topic is I/O buffering, in which we will look at what buffering is and what types of buffers can we have. Reading a block of data from disk. Suppose that a user process wishes to read a block of data from a disk one at a time having a length of 512 bytes. The data is to be placed within the address space of the user process at location 1000 to 1511. We execute an IO command read block 1000 disk to the disk unit and then wait for the data to become available. The waiting could be either busy waiting which is continuously testing the device's status, or the process will be blocked till the arrival of an interrupt. There are two problems with this approach. The program is hung up waiting for the relatively slow I/O to complete. This approach interferes with swapping decisions by the operating system. Virtual locations 1000 to 1511 must remain in main memory during the block transfer. Otherwise, some of the data may be lost. If paging is being used, at least the page containing the target locations must be locked into main memory. Thus, although portions of the process may be paged out to disk, it is impossible to swap the process out completely, even if this is desired by the operating system. Buffering. If a block is being transferred from a user process area to an I/O module, then the process is blocked during the transfer and the process may not be swapped out. To avoid these overheads and inefficiencies, it is sometimes convenient to perform input transfers sometime before the request is made and to perform output transfers sometime after the request is made. This technique is known as buffering. There are two types of I/O devices: block oriented and stream oriented. A block oriented device stores information in blocks that are usually of fixed size, and transfers are made one block at a time. Generally, it is possible to reference data by its block number. A stream-oriented device transfers data in and out as a stream of bytes with no block structure. Pause the video and find the answer to task 1. Give at least 2 examples each for the two types of I/O devices that I just mentioned. Let us now talk about single buffer. When a user process issues an I/O request, the operating system assigns a buffer in the system portion of main memory to the operation. This means that the buffer is placed in the portion of memory where the operating system resides. Input transfers are made to the system buffer. For block-oriented devices, when the transfer is complete, the process moves the block into user space and immediately requests another block. This is called reading ahead or anticipated input. It is done in the expectation that the block will eventually be needed. This is a reasonable assumption most of the time because data are usually accessed sequentially. Only at the end of a sequence of processing will a block be read in unnecessarily. Here you see two pictures. The first picture is where you have no buffer. So a user process asks for data from an I/O device and the I/O device is providing data and the operating system is simply forwarding that data into the address space of the requesting process. In the second picture, we use a single buffer. Note the location of the buffer. It is present in the space of the operating system. So first data goes from the I/O device to this buffer and then it is moved from this buffer to the address space of the requesting process. This approach will generally provide a speed up compared to the lack of system buffering. What we are trying to say is that single buffering will be a faster operation than the no buffering approach. The user process can be processing one block of data while the next block is being read in. The OS can swap the process out because the input operation is taking place in system memory rather than user process memory. The OS must keep track of the assignment of system buffers to user processes. If the I/O operation involves the same disk that is used for swapping, it hardly makes sense to queue disk writes to the same device for swapping the process out. This attempt to swap the process and release main memory will itself not begin until after the I/O operation finishes, at which time swapping the process to disk may no longer be appropriate. For block-oriented output, when data are being transmitted to a device, they are first copied from the user space into the system buffer, from which they will ultimately be written. The requesting process is now free to continue or to be swapped as necessary. Performance comparison between single buffering and no buffering. Assume time required to input one block is T. Computation time between input requests is C. Without buffering, execution time per block is T plus C. This is the time we spend on working with the block that we have just received. Continuing with performance comparison. Consider a system with a single buffer. Time required to input one block is T. That is, we take T seconds to bring a block from the input device to the system buffer. With single buffer, assume time required to move the data from the system buffer to user memory is M. We take M seconds to move the block from the system buffer to user space. Computation time between input requests is C. This is the first block. After the first block is in the user space, two things happen together. Data transfer from the input device to the system buffer for the second block and computation on the first block. So C and T overlap for consecutive blocks. If T is larger than C, we will complete computation on the first block, but the buffering of the second block will still be going on. So the total time that we will spend on a block will be T plus M. Let us continue the same example. Bring a block from the I/O device to the system buffer and then move it from the system buffer to the user process. Now, if C is larger than T, we will complete buffering of the second block, but the computation on the first block will still be going on. So the total time that we will spend on a block is C plus M. So with a single buffer, execution time per block is maximum of C or T plus M. In most cases, execution time per block is substantially less with a single buffer compared to no buffer. Single buffer and stream oriented I/O. For stream oriented I/O, the single buffering scheme can be used in a line at a time fashion or a byte at a time fashion. Line at a time. Line at a time operation is appropriate for scroll mode terminals, sometimes called dumb terminals. User input is one line at a time with a carriage return signaling the end of a line, and output to the terminal is one line at a time. A line printer is another example of such a device. The buffer can be used to hold a single line. The user process is blocked during input, awaiting the arrival of the entire line. For output, the user process can place a line of output in the buffer and continue processing. It need not be blocked unless it has a second line of output to send before the buffer is emptied from the first output operation. Byte at a time. Byte at a time operation is used on forms mode terminals when each keystroke is significant and for many other peripherals such as sensors and controllers. In the case of byte at a time IO, the interaction between the operating system and the user process follows the producer-consumer model. During input, the operating system places a byte in the buffer from the device and the user process consumes it. During output, the user process places a byte in the buffer and the operating system consumes it and passes it to the device. Here you need to pause the video again and tell me what is a forms mode terminal. Double buffer. An improvement over single buffering can be had by assigning two system buffers to the operation. A process now transfers data to or from one buffer while the operating system empties or fills the other. Notice that we first transfer from device to the upper buffer and from the lower buffer to the process. Then next, we transfer from device to the lower buffer and from the upper buffer to the process. This technique is known as double buffering or buffer swapping. Double buffer and block oriented IO. Let us assume T equals M. This means the time to transfer a block from device to system buffer equals the time to transfer a block from system buffer to user space. So M gets overlapped with T for consecutive blocks. For block-oriented transfer, we can roughly estimate the execution time as maximum of C or T. If T is greater than C, that is the transfer time is greater than the computation time, the process completes computation of the first block, but the second block is still being transferred to the system buffer. So we must wait T seconds for the availability of the second block. It is possible to keep the block-oriented device going at full speed if T is greater than or equal to C. The device can transfer without delays between consecutive transfers because the process computes in lesser time than the transfer time. If T is less than C, the second block arrives completely into the system buffer, but the process is still computing the first block. So the second block will be used by the process after C seconds. If T is less than C, double buffering ensures that the process will not have to wait for the IO device. The data will be ready because the process is taking longer in computation. In either case, an improvement over single buffering is achieved at the cost of increased complexity. Double buffer and stream oriented IO. We again assume that T equals M, and this means that the time to transfer a block from device to system buffer equals the time to transfer a block from system buffer to user space. So M gets overlapped with T for consecutive blocks. For stream oriented input, we have two alternative modes of operation. For the line at a time IO, if T is greater than C, the process finishes computation of the first line, but the second line is still being transferred. So the process gains access to the second line after T seconds and blocks for T minus C seconds after computing the first line. For line at a time IO, if T is less than C, the second line is transferred earlier, but the process is still busy in computation of the first line. So the process accesses the second line after C seconds. The user process need not be blocked for input or output unless T is greater than C. So it will finish computation and then it will block until the next line become accessible. For byte at a time operation, the double buffer is equivalent to a single buffer of twice the length. Think about it. In both cases, the producer-consumer model is followed. Circular buffer. A double buffer scheme should smooth out the flow of data between an I/O device and a process. If the performance of a particular process is the focus of our concern, then we would like for the I/O operation to be able to keep up with the process. Double buffering may be inadequate if the process performs rapid bursts of I/O. That is, it asks for I/O again and again within a short span of time. In this case, the problem can often be solved by using more than two buffers. When more than two buffers are used, the collection of buffers is itself referred to as a circular buffer, with each individual buffer being one unit in the circular buffer. So we have a buffer of buffers. When we transfer the first block from the device, it goes into the first system buffer. When we transfer the second block, it goes into the second system buffer. Continuing, suppose we have n buffers in total. When we transfer the nth block from the device, it goes into the last system buffer. When we transfer the n plus 1th block from the device, it goes into the first system buffer. The process will go in the same order. After the first block has been brought in, the process picks it from the first system buffer. After the second block has been brought in, the process picks it from the second system buffer. After the nth block has been brought in, the process picks it from the last system buffer. After the n plus 1th block has been brought in, the process picks it from the first system buffer. This is simply the bounded buffer producer-consumer model. The utility of buffering. Buffering is a technique that smooths out peaks in I/O demand. However, no amount of buffering will allow an I/O device to keep pace with a process indefinitely when the average demand of the process is greater than the I/O device can service. That is, when C is very small as compared to T, when the process computes in negligible time and the time to transfer from the I/O to the system buffer is very large. Even with multiple buffers, all the buffers will eventually fill up and the process will have to wait after processing each chunk of data. However, in a multi-programming environment where there is a variety of I/O activity, there are many I/O devices and a variety of process activity to surface because there are many processes in the memory. Buffering is one tool that can increase the efficiency of the operating system and the performance of individual processes. We now turn to disk scheduling, where we will examine its performance parameters and talk about various scheduling policies. Let's first talk about a point of concern. The speeds of processors and main memory have increased far more rapidly as compared to the speed of the disk. Disks are currently at least 4 orders of magnitude slower than main memory. That is, main memory is 10,000 times faster than the disk. This gap is expected to remain in the future. The performance of disk storage subsystem is of vital concern, and much research has gone into schemes for improving it. Disk performance parameters. When the disk drive is operating, the disk is rotating at constant speed. To read or write, the head must be positioned at the desired track and at the beginning of the desired sector on that track. Track selection involves moving the head in a movable head system or electronically selecting one head on a fixed head system. On a movable head system, the time it takes to position the head at the track is known as seek time. Once the track is selected, the disk controller waits until the appropriate sector rotates to line up with the head. The time it takes for the beginning of the sector to reach the head is known as rotational delay or rotational latency. The sum of the seek time, if any, and the rotational delay equals the access time, which is the time it takes to get into position to read or write. Once the head is in position, the read or write operation is performed as the sector moves under the head. This is the data transfer portion of the operation. The time required for the transfer is the transfer time. In addition to the access time and transfer time, there are several queuing delays normally associated with a disk I/O operation. When a process issues an I/O request, it must first wait in a queue for the device to be available. Finally, the device is assigned to the process. If the device shares a single I/O channel or a set of I/O channels with other disk drives, then there may be an additional wait for the channel to be available. At that point, the seek is performed to begin disk access. In some high-end systems for servers, a technique known as rotational positional sensing or RPS is used. This works as follows. The process waits for I/O device, which is the disk, to be available. Then it waits for the I/O channel to be available. Then it tells the I/O device the block or set of blocks it needs and generates the seek command. When the seek command has been issued, the channel is released to handle other I/O operations because the disk controller will work now. When the seek is completed, the device determines when the data will rotate under the head. As that sector approaches the head, the device tries to re-establish the communication path back to the host. That is, the device tries to grab an available I/O channel for data transfer. If either the control unit or the channel is busy with another I/O, then the reconnection attempt fails and the device must rotate one whole revolution before it can attempt to connect, which is called an RPS miss. So if we are using rotational positional sensing, we need to add the delay of the RPS miss to all the delays shown in the figure above. Seek time. Seek time is the time required to move the disk arm to the required track. It is difficult to estimate seek time. Seek time consists of two key components. the initial startup time, and the time taken to traverse the tracks that must be crossed to get to the desired track called the traversal time. Improving seek time. Unfortunately, the traversal time is not a linear function of the number of tracks, but includes a settling time, time after positioning the head over the target track until track identification is confirmed. Much improvement comes from smaller and lighter disk components. Some years ago, a typical disk was 14 inches in diameter, whereas the most common size today is 3.5 inches, reducing the distance that the arm must travel. A typical average seek time on contemporary hard disks is under 10 milliseconds. Rotational delay. Rotational delay is the time required for the addressed area of the disk to rotate into a position where it is accessible by the read-write head. Disks rotate at speeds ranging from 3600 rpm up to 15,000 rpm. At 15,000 rpm, there is one revolution per 4 milliseconds. We take the reciprocal of the revolutions per minute and then multiply by 60 to get the time of a revolution in seconds. So in 4 milliseconds, I can rotate the disk 360 degrees. The point that was under the head will come back under the head after a full rotation. Any point on the disk can be accessed either by rotating clockwise or counterclockwise. Then in the worst case, to get to a certain point, I will have to give the disk a half rotation. I can say that the largest rotation happens when I rotate the disk by 180 degrees, clockwise or counterclockwise. On average, the rotational delay will be 2 milliseconds. This is the delay to rotate the disk by 180 degrees, or this is the time I need to give the disk half of a full rotation. So rotational delay is the reciprocal of 2 times r, where r represents revolutions per second. Transfer time. The transfer time to or from the disk depends on the rotation speed of the disk. We say that T is B divided by Rn, where T is the transfer time, B is the number of bytes to be transferred, N is the number of bytes on a track, R is the rotation speed in revolutions per second. The total average access time TA can be expressed as a sum of the seek time, the rotational latency, and the transfer time. TA is TS plus 1 divided by 2R plus B divided by Rn. What did we gather so far? We looked in detail at design issues involved in the I/O function of an operating system. We discussed the logical structure of the I/O function. We understood the concept of buffering. We delved into different forms of buffering. We discussed disk scheduling. At the end, as always, I leave you with some things to do, like read, read the book, find the answers to the tasks that I have set you, and I will ask you to submit the Word files via Google Classroom. Note the questions that you have in your mind regarding this lecture and keep them with you when we sit for the relevant online session. Email me any suggestions that you have relevant to content or quality of this lecture. Take care of yourself. We'll meet again. Allah Hafiz.